Hello! This video is about viewing cyclotomic polynomials visually. I find visuals to be a very useful tool for understanding math topics, and recently, while thinking about cyclotomic polynomials, I thought of a way to visualize them. And these visualizations helped me to gain a better understanding of them, but they also raised a lot of new questions that I wouldn't have had otherwise. And that's what I'd like to share with you today. So first, let's have an introduction or refresher to cyclotomic polynomials. And we'll do this thinking about these four numbers: 1, -1, I, and -I. What do they have in common? Well, when you raise them to the fourth power, they equal 1. And maybe we'd write this instead as x to the fourth minus 1 equals 0. This is nicer because there's a 0 on one side of the equation. And so these four numbers above set that left side to 0, which means we can factor the left side. We can say x to the fourth minus 1 equals x minus 1 times x minus -1 times x minus I times x minus -I. And this is a useful factorization. It helps us to clearly see what the zeros are, but it relies on using I and -I. What if we want a factorization that stays within the rational numbers? In that case, we'd have to multiply the 2 on the right to get x squared plus 1. And now we have a factorization that only uses irrationals. And these factors on the right side are minimal polynomials over the rationals, which means that they're the furthest we can break that down into. Similarly to how an integer can be broken down into its prime factors, a polynomial can be broken down into its minimal polynomials. And knowing that factorization tells us a lot about the polynomial. Okay, so we have these minimal polynomials, but where did they come from? Can we understand that a bit better? Well, these four numbers are called the fourth roots of unity, because when raised to the fourth power, they equal 1. But they don't all act the same. The 2 on the right are called primitive fourth roots, because 4 is the smallest number for which they are a root of unity. But -1 is a primitive second root. If you square it, it equals 1. That's not true for I or -I. And then 1 is the primitive first root. It already is 1 itself. And so those minimal polynomials at the top came by combining primitive roots of the same order. And we call them the cyclotomic polynomials. And we write that using the Greek letter phi, with a subscript to denote which primitive roots created it. So here we have phi sub 1, then phi sub 2, and phi sub 4. Now here we did this with x to the fourth minus 1 and the fourth roots of unity, but this applies to any nth roots of unity. Let's take a look at another example. So here we have the 10th roots of unity. You can see them on the right, 10 evenly spaced points around the unit circle. And here zeta is 1/10 of the way around. And again, we can factor x to the 10th minus 1 into x minus 1 times x minus zeta times x minus zeta squared, and so on. But if we want a factorization that remains in the rationals, we need to combine primitive roots of the same order. So the primitive first root gives us phi sub 1, the primitive second root gives us phi sub 2, the primitive fifth roots gives us this phi sub 5, and finally phi sub 10. So now we have a background on where these come from, but what do they tell us, and how can we visualize them? We'll take phi sub 10 for example. So this is the minimal polynomial for the primitive 10th roots. And that means that if we input a primitive 10th root, we will get 0. So let's do that. Here on the left, we have the 10th roots of unity, and we'll take phi sub 10 of zeta. So that gives us zeta to the fourth, we'll put a point there, then negative zeta cubed, zeta squared, negative zeta, and finally 1. Now, two of these points, the ones in red, are negative, but we can turn those positive by multiplying by -1, which will send them across the unit circle. And that leaves us with 5 points that make a regular pentagon. Now, we said that inputting zeta would give us 0, and we have these 5 points, but it makes sense that the sum of these 5 points is 0. It's a regular pentagon centered at 0. These points are kind of all evenly spaced around 0. And I like this way of thinking about this polynomial and the relationship it has with its zeros. So we'll call this pentagon the shape of 10. And furthermore, the shape of n is the set of points produced by phi sub n of zeta to the s, with zeta to the s being some primitive nth root. And importantly, the sum of these points is 0. So we should expect them to be pretty evenly distributed around 0. So let's take a look at some of the shapes of early cyclotomic polynomials. 1 and 2 are pretty boring. They just give us a line between 2 points. And the same is true for 4 and 8. 3, not surprisingly, gives us a triangle. And we get a triangle from 6, 9, and 12 as well. 5 and 10 are pentagons. 7 and 14 are heptagons. And then 11 and 13 are 11gon and a 13gon. But then 15 gives us this shape, which is not a regular polygon. Things kind of go astray here. So why did that happen? Before we go to that question, maybe we want to ask, why didn't it happen earlier? For example, why is the shape of 6 a triangle instead of a hexagon? Maybe we would expect to get a hexagon because it's 6. But it turns out if you have the shape of an odd number, doubling that number won't change the shape. Or more formally, given an odd integer k, phi sub 2k has the same shape as phi sub k. And we can show this using the fact that phi sub 2k of x equals phi sub k of negative x. For example, here is phi sub 5, and here is phi sub 10 of x. And you can see the odd degree terms are negated, while the evens are not, since -1 to an even degree is 1. The other fact we need is that zeta is a primitive 2kth root if and only if negative zeta is a primitive kth root. So taking phi sub 2k of zeta is the method we defined to get the shape of 2k. But using the fact on top, that's the same as taking phi sub k of negative zeta. But by the second fact, negative zeta is a primitive kth root, which means this is also the method by which we get the shape of k. So these shapes are produced by the same method, so they must be the same. Okay, so that explains why the shape of 6 is a triangle, but why is the shape of 9 a triangle instead of a nonagon? Well, in this case, it turns out that that's because 9 is 3 times 3. But we only take one of those 3's into account when determining the shape. More generally, given a prime p, phi sub p to the nk has the same shape as phi sub pk. If a number is divisible by p, further multiplying by p doesn't change the shape. And this we see very similarly. Here, phi sub p to the nk of x is equal to phi sub pk of x to the p to the n minus 1. For example, here is phi sub 10, and here's phi sub 40. We multiply by 4, and we see that all of the exponents have been multiplied by 4. Okay, so this is our first fact. The second is that if zeta is a primitive p to the nkth root, then zeta to the p to the n minus 1 is a pkth root. This is the expression by which we get the shape of p to the nk, but by the first fact above, that's equivalent to taking this expression. But by the second fact, zeta to the p to the n minus 1 is a pkth root, so this is also the method by which we get the shape of pk, so these shapes are equivalent. Which means that if we let a have this prime factorization, and then a prime be just one power of each of those primes, then the shape of a equals the shape of a prime. And we can show that by recursively using the fact at the top. Using the equivalence of the shape of 2k and the shape of k, we can show that if A star is only the odd primes, then the shape of A equals the shape of A star. And this means that if we want to study the shapes for all integers, we can focus on sets of distinct odd primes. Okay, well maybe what's the first thing to look at? The simplest case is no odd primes. So for this, let's look at phi sub 1. And that is x minus 1. And if we take 1 as an input, we get 1 and negative 1 as our points, which gives us a shape that's just a line. So the shape of any 2 to the n is a straight line. It's just the points 1 and negative 1. Okay, the next case is if we have one odd prime. In this case, phi sub p is x to the p minus 1 plus x to the p minus 2 plus all the way down to 1. It's all of the powers of x less than p. And if we take zeta as an input, we just get all of the pth roots, which are p points spaced evenly around the unit circle, which means that we get a p-gon. So the shape of any 2 to the n times p to the m is a p-gon. And this is why 3, 6, 9, and 12 all gave us a triangle. Now we'll move on to the next case, which is multiple odd primes. And here, the shapes are more complex. There's no simple rule that we can define as with the previous cases. And the first number with multiple odd primes is 15. It's 3 times 5. And that's why we saw that irregular polygon. So let's dive into that. Here we have the unit circle with the 15th roots of unity. And this is phi sub 15 of zeta. So if we plot these points, and then we send the negatives to the opposite side, we get this shape. It isn't regular, but the points are spread fairly evenly around 0. It does make sense by looking that these points would add to 0. But is there a better way that we can understand that? Here is the shape of 15 on the left, and here is just the points on the right. And we can connect 3 of them using a regular pentagon, which we know the sum of the points is 0. But 2 of those points are not part of our shape. We don't want them. But that's not a problem. We can add in a triangle that connects 2 of the other points. And again, we get a point we don't want. But this new point is the negative of one of the unwanted points from the pentagon. So the sum of these two is 0, which means we can remove them from the shape and the sum will still be 0. Now we'll repeat this, add a triangle again, and remove 2 points with a 0 sum. And so we can see that this shape is kind of constructed out of a pentagon and 2 triangles. Now going forward, I'm going to display this shape like this by fading out those lines that connect to a missing point. So this is the shape of 15, right? Well, what if we take zeta squared as an input? On the right, we see the resulting terms from that. And if we place them on the unit circle, they appear here. And then we can turn the negative ones positive. And then we get these points. And when connected, they look like this. So this is the shape from taking phi sub 15 of zeta squared. And again, if we take just those points, we can connect them using a pentagon and 2 triangles. But it's different than before. Phi sub 15 has 2 shapes. The shape on the left is produced when we take phi sub 15 of zeta, zeta to the 4th, or one of their inverses. The shape on the right is produced by zeta squared, zeta to the 7th, or one of their inverses. So maybe we can't say that each number has a shape, but we can still say that each number has a family of shapes. And we do see that these two are very similar. Each is made up of a pentagon and 2 triangles, and each triangle cancels 1 point from the pentagon. The only difference is that on the left, those 2 missing points on the pentagon are adjacent, while on the right, they're not adjacent. And that kind of makes sense. If you pick 2 points from a pentagon, they can either be adjacent or non-adjacent. So it's not surprising to see that both of these appear. But maybe now we want to see what happens in other cases. So here is phi sub 21, which is 3 times 7. And here we get 3 shapes, but all of them have a heptagon and 2 triangles. The only difference, again, is which 2 points are missing. On the left, we have adjacent points. In the middle, they're separated by 1. And on the right, they're separated by 2. So we can guess that maybe the shape of 3 times p is going to give us a p-gon, 2 triangles, and then it will have a bunch of shapes based on how you can pick 2 points on those p-gons. So let's take a look at phi sub 33, 3 times 11. Here our guess runs into some problems. First off, we see these have 4 triangles. We don't always use 2. They do all have one 11-gon, but if you're going to pick 4 symmetric points on an 11-gon, there are 10 options to do that. And we only see 5 shapes here. Half of the possibilities don't show up as one of these shapes. And if we move further to phi sub 39, again we see 4 triangles. And here there are 15 ways to pick 4 points on a 13-gon, but we only see 6 of them. And if we move to phi sub 51, we have 6 triangles now. And at this point I have to remove those faded lines, otherwise it gets too messy. So now we have some questions. Does this pattern continue? Do we always get related shapes that have a p-gon and a bunch of triangles? And if we do, what determines the number of triangles? And what determines the number of shapes? The top 2 questions we can answer fairly simply, and we'll do those together. So we'll let p be a prime that's bigger than 3, and we'll say that p equals 3k plus or minus 1, depending on its equivalence class mod 3. The shapes of 3p can be constructed from 1 p-gon and k triangles. This is why 5 and 7 gave us 2 triangles, because they're adjacent to 6, which is 3 times 2. And then 11 and 13 gave us 4 triangles, because they're adjacent to 12, which is 3 times 4. But how do we show that this is true? Here we'll look at the case of p equals 3k plus 1, and then 3k minus 1 is very similar. So the coefficients of phi sub 3p follow a pattern. 1, negative 1, 0, 1, negative 1, 0. Repeats until the middle where we have a 1, and then the pattern reverses. 0, negative 1, 1, 0, negative 1, 1. And more explicitly, phi sub 3p equals this expression. Now, if we take zeta as an input, if we just take the blue terms, we see that they're all separated by zeta cubed. And zeta is a 3pth root, which means that these form 2k plus 1 points of a p-gon. But p is 3k plus 1, which means there are k missing points from the p-gon, which are these points above. But that's not a problem, because we can form k different triangles given some r between 1 and k, where these are the 3 points of the triangle. The point on the left is the negative of one of the points missing from the p-gon. The point in the middle appears in the left half of phi sub 3p, and the point on the right appears in the right half. So we have a p-gon, k triangles, we've accounted for all the points in the polynomial, and each of the red points has a corresponding negative to cancel it out. But this just shows the case where we're taking regular old zeta. What about any of the other primitive roots? Well, let's suppose that zeta to the a and zeta to the b are part of a d-gon, where d divides 3p. So this might either be a triangle or a p-gon. We'll treat it generally. That means that zeta to the a minus b is equal to 3p over d times some r. Now, if we produce a shape using the primitive root zeta to the s instead of just zeta, then the distance between those points now is going to be zeta to the s to the a minus b. We can flip those exponents, and we know we can replace zeta to the a minus b, and we end up with this result, which tells us that these points are still part of a digon. And because zeta to the s is primitive, the points don't become the same. They're still separate points on the digon. So all of the points on the p-gon will still be on a p-gon. All of the points on each triangle will still be on a triangle, which means the shapes of 3p can be constructed from one p-gon and k triangles. But now we come back to that other question: how many shapes are there? Let's take a look at some examples. Phi sub 87 arises when p is 29, and we get 14 shapes. With p being 31, we get 15 shapes. And then here are the next few primes. And what we see is that the number of shapes is equal to p minus 1 over 2. And this is always true. P minus 1 over 2 is the number of shapes in the family of phi sub 3p. But how can we show this? Let's take a look at the shapes of phi sub 87. The one in the top left is produced by zeta. And if we look at phi sub 93, we see a very similar shape produced by zeta. It creates this kind of U. And with phi sub 111, we also see a U being produced by zeta. Now let's jump back to phi sub 15, where this was our U shape. And this was generated by zeta, but also zeta to the fourth, zeta to the negative 4, and zeta to the negative 1. And visually, this is where those points are. Now if we look at phi sub 21, this is our U shape, and these are the points that generate that. And we see they're in a very similar position. And if we look at the positions that generate this U shape for a lot more, we see a very similar pattern. There are 2 points that get closer and closer to 1, and then the other 2 points are a third of the way around the circle. And it turns out that when p equals 3k plus or minus 1, these 4 points always produce that U shape, and they're the only points that produce that U shape. Suppose that 2 points are adjacent on a p-gon produced by zeta to the s. In other words, zeta to the s to the a minus b equals zeta cubed. They are also adjacent when produced by s times p plus or minus 1. And we can show that. Here, we just rearrange the exponents, and then we can substitute zeta cubed from above, and we see that this equals zeta to the 3p plus or minus 3. But zeta is a 3pth root, which means that just equals zeta to the plus or minus 3. So in both cases, these points are separated by zeta cubed, so they're still adjacent on that p-gon. And we showed this for p plus or minus 1, but they are also adjacent when produced by zeta to the negative s. And because adjacent points stay adjacent, that means that the p-gon is invariant when points are raised to the negative 1 or p plus or minus 1. And if we combine those, we can say or negative p minus or plus 1. Now the p-gon is invariant, but what about the triangles? The missing points on the p-gon determine the triangles, so the entire shape is invariant. And that means that for every zeta to the s, there are 3 other primitive roots that produce the same shape. And we get that by multiplying s by one of those values in the second line. So that tells us that each shape has 4 primitive roots that produce it. And that's why the U shape was always produced by these 4 roots. So we know that each shape has 4 roots. How many 3pth roots of unity are there? Well, we get that from the totient function. We take the totient of 3p, because every number co-primed 3p gives us a primitive root. And that equals 2 times p minus 1. So each shape is produced by 4 roots, which means the number of shapes is this, which equals p minus 1 over 2. So once again, phi sub 3p has p minus 1 over 2 shapes. Okay, so that answers the big questions, but now we can have some fun. Can we categorize these shapes? Let's look at phi sub 87 again. And we see one of these kind of looks like a triangle, and the next one kind of looks like a square. And then we get a pentagon and some further shapes. Okay, what about phi sub 93? Again, we have these kind of shapes appearing. And phi sub 111, we see them again. So what is causing this? What roots give us these shapes? And what about that bottom row? Why are those different? Well, this video is pretty long already, so we will take a deeper dive in the next video. And the biggest topic there is to move away from 3p and instead look at phi sub pq, where p and q are any two different primes. And here, things get even more complicated. So the shapes from 5 times 7 can be constructed with 3 pentagons and 2 heptagons. And then 5 times 11 from 2 pentagons and an 11gon? 11 is simpler than 7. Okay, what about 13? That's from 5 pentagons and 2 13gons. And then for 17, we need 7 pentagons and 2 17gons. And then 19, only 4 pentagons and 1 19gon. For some reason, 11 and 19 are simpler than the rest. We'll talk about why that is in the next video, but maybe see if you have a guess about what's going on. The answer is related to the work we did with 3 times a prime. But anyway, thanks for watching. I hope this helped you understand cyclotomic polynomials a little better and appreciate the fun we can have when visualizing math.